So this is 4-3 alpha lesson. We start with the learning objectives, using derivatives, solving problems, related rates is later in the chapter. Optimization, that's what we're looking at here. Optimization meaning local and global names and maps. Okay? So we're telling you, for the derivative, if the derivative goes from negative to positive, that's telling you a local name. That should make sense to you. If the derivative is negative, then it's forward. And if the derivative switches to positive, it's rising. So in between, you have a local name. And if it goes from positive to negative, that happens in a local max. All right? And there's a picture in the book, which is kind of helpful. On page 205. Okay? Not going to the whole thing. Right? We're telling you that in this case, as we start from the left, between A and C sub 1, F prime is greater than 0. Derivative is positive, it's going up. Now what happens? At C sub 1, the C's are between A and B as well. But at C sub 1, the derivative equals 0. But on the other side, the derivative is still positive. So that can happen. Just because the derivative is 0 does not mean you have a local local max. If you have a local local max, then the derivative is 0. But it's a converse error to exchange what's front of it, what's in front of that. Now we go to the next point. The derivative 0, and then before that to the left was positive, to the right is negative, yes. We have a local max. The derivative went from positive to negative. And up here, the derivative fails to exist. Another critical point. We're not going to the whole picture, but that's something to come back to. If we get to example 1. Ready? This is pretty user friendly. You have this cubic. So you differentiate it, you get a quadratic. The greatest common factor on both sides of that subtraction sign of 3 is factor this 3 out, and you end up with this quadratic, which is the difference of squares. So what makes the derivative 0? -2 and 2. So I'm going to build the table. In my table, I put -2 and 2. I'm ignoring this. I'm ignoring the y column. I'm just trying to understand what's going on here. So -2 and 2, the derivative is 0. Good? Then what? Well, I went to the left of -2. I put -3 into the derivative. I got a positive value. I went to the right of -2, got a negative value. The derivative went from positive to negative, increasing to decreasing. So that's a local max. At 2, I already know the derivative is -0. I go past 2, go to 3, it's positive. This is a local min, because the derivative is negative, the graph is falling, then it begins to rise. Now, the other thing you could do, which we didn't get to yet, you have to think about this, the second derivative test, which you read about, the section, if I take the second derivative of this thing, you would get 6x. If I put these numbers in here, -2 in the second derivative gives you a negative number. +2 is a positive number. What does the second derivative tell you? It tells you the concavity of the graph. The cavity is an opening up or down? Is the graph smiling or is it frowning? What's happening? If the second derivative is positive, the graph is concave up. So the second derivative is 6x. 6x times 2 is positive. So this happens confirming you have a min there. Because the graph would be concave up away from a min. And it would be concave down away from the max. You don't need to do both. They're good. They're not going to contradict the first derivative past the second derivative. Here's the other example for B, which is a little harder than the cubic. So you have this, x squared take away 3 times e to the x. You get the derivative. What do you do? The first term times the derivative of e to the x is itself. Plus the derivative of the first term, which would be 2x plus 0 times e to the x. If you look up here, e to the x is a factor of both sides of this addition sign. You factor it out, and you're left with this quadratic, which you can factor the lattice. E to the x can't be 0. There's no exponent there. It's e to the x can be 0. So what makes this thing 0 would be negative 3 and 1. So here's the number lines. Right? If you just write them on the number line, what you're doing is you're testing points, which is what we did here. You're testing points to the left of the values you identified on the number line, in between them, and to the right of them. So I know that negative 3 and 1 make the derivative 0. If I put negative 4 in there, right? E to the negative 4 is still going to be positive. It's going to be a small number. X plus negative 4 plus 3 is a negative. Negative 4 plus negative 1 is a negative. Positive times a negative times a negative is a positive. The derivative is positive. 0 gives you a negative. You got to check the sign change. So in between, you had a max. Because it was going up and then going down. Going down, put 2 in there, but it goes up. Never min. Okay? So we're talking about doing these problems analytically without a calculator. We'll leave it up there. That's your model. You're going to problem 3. Okay, problem 3. What happened? Y is 4th degree. The derivative is 3rd degree. The greatest common factor on both sides of the subtraction side is 8x. And you have to consider the square. So this is 3rd degree. How many zeros does it have? 3. How many are real? 3 or 1. In this case, it is 3. 0 would make 8x 0. Negative 1 and 1 would make, it's in the parentheses 0. And here's your number line. And you're going to test points to the left of negative 1, between negative 1 and 0, between 0 and 1, to the right of 1. So here's my zeros in my table. Negative 1, 0, 1. Well, ready? Let's go to the second derivative. It's going to be easier than putting decimals in there without a calculator. Does that make sense? Like without a calculator, I want to make this efficient. So the second derivative is 24x squared. So I pick negative 2. Negative 2, when you square it, positive. This value is positive. I'm sorry, just put it right on the test. Sorry, test that. Put negative 1 in here. Negative 1 is a positive output. Positive means the graph's concave up. So that's telling you you have a local min. Put 0 in here. It's giving the second derivative a negative. You have a local max with the graph's concave down. You put 1 in here, you get a negative. That means the graph is concave down, and that's how it behaves. I'm sorry, put one in here, I got a positive, right? So positive value is how it's concave up, and that's how it behaves better. So concavity, right? And this is from the table, top right of the table to the top. If the derivative goes from negative to positive, it's going from concave down to concave up. The second derivative goes from positive to negative, it's concave up or down. So that is an inflection point, which you can think of essentially as like you have these two spoons. And the spoons were tipping. This one's concave up, that's concave down. That's a point of inflection. So 2b, we have this. We have a graph of 3 plus sine x. In 2b, they're asking use the concavity test to determine the cavity of functions on this interval from 0 to 2 pi. Well, really, it's ready. Y equals 3 plus sine x. It's just a shift up 3. It's got nothing to do. When I differentiate, it seems that I differentiate to 0. So the first derivative is cosine. The second derivative is negative sine. You're looking for when the graph changes concavity. If I look at the sine wave, this is the negative sine wave, so it's going down through the origin. What is the negative sine wave going to be equal to 0? In terms of the circle, 0 here, and n pi. Okay? The interval is 0 to 2 pi. Exclusive parentheses, 0 to 2 pi don't count. So the only point in the interval where the sign is 0 is at pi. What happens? Well, again, here's this number line. We're going to use the number. Take a value between 0 and pi. What's happening? The sign, the y value from 0 to pi is positive. If you have negative sign, so you have a negative value, which is telling you the graph is concave down. Between pi and 2 pi, the sign's negative, so the opposite sign would be positive, would be concave up. And you would have point of inflection at pi. Make sense? So the second derivative is used for 2 things. You can use it for a maximum thing, depending on whether the second derivative is positive or negative. You also use the first derivative, that's the local maximum thing. But you need the second derivative to, so the second derivative equals 0. You have potential points of inflection. You need to confirm the sign. So that's up there. You're going to problem number 7. All right, so let's look at 7. Now, just think about this before you start writing. parent graph is a cube. The derivative is a quadratic. So the second derivative is going to be linear. The fundamental theorem of algebra is telling you I'm zero. Got 1, 0. So what makes this thing 0? When you factor out the greatest common factor of 6, so this equals 0 by adding a -7 to both sides divided by 4, you have -7/4. So I go to the second derivative and pick a number to the left of -7/4. -2. -2 would give you -48 plus 42. It would give you a negative. That's telling you the graph is concave down. -1 is giving you -1 times 24 plus 42 concave up. You do a point of inflection. So we go to the calculator, which is not the first source. I'm using a non-calculator question. To see what's happening here, we go to y equals and you have 4x cubed plus 21x squared plus 36x plus a -20. So we got a table set. These numbers, ready? You're not going to see this because the numbers are really high. Where's the concavity change? Between 737 and 0. Well, that was the issue. It's hard to see this. You can't push graph. So, all right, let's make the Y max 800. Okay, so the graph, it's not a good window, is concave down, and then it's going to begin to be concave up, which you can't see in that picture. That was the issue. He gave you numbers that you're not going to be able to tell just by looking at the picture. All right? So, if you're at home